Good morning, students. In today's video lecture, we will see what is sampling and what is sampling theorem. Sampling theorem is very important, but this small or short video lecture will be in your examination point of view. There is a lot more to study about sampling and sampling theorem. You will be studying in communication systems or in the higher order subjects. Okay, so let us study what is sampling and how it is important. So, what is sampling is when you convert an analog signal into a digital signal, sampling is the first step. So you know that many of the signal processing are done in the digital domain, not in the analog domain. Okay, even though the signals are physically available signals are analog in nature, you convert it into a digital signal and then you process it because it is easy, and in the digital domain you have a lot of advantages. Okay, so most of the signal processing is done in the digital domain. So all the analog signals available in nature, okay, for processing, you need to convert it into a digital domain. For example, an audio signal or a video signal, okay, a camera signal. Now you have digital cameras, but these signals, when they physically occur, the images, okay, they are all analog in nature and they have to be converted into a digital signal and then into samples, and then they will be processed. So in this process, that is in the process of analog to digital conversion, sampling is the first step. So sampling is the first step, and you have two more steps before getting a digital signal. The other two steps are called as quantization and encoding. Okay, it is out of scope of this particular subject. So sampling is the first step in converting an analog signal into a digital signal. Okay, after that you have quantization, where you convert it into a discrete time signal, and then you have to code it in the binary form to get an actual digital signal. Okay, so these are all you can go in depth into the other steps, all these three steps. Okay, ADC is a area of research, so much is going on in real time ADCs, in implementation of ADCs and using ADCs and so on. Now we'll see what is sampling and what is sampling theorem. So sampling is nothing but converting your analog signal into a discrete time signal or a continuous time signal like x of t. Continuous time signal like x of t is converted into a discrete time signal, which can be called as x of n. Okay, so now how it is done is, this x of t will be usually multiplied by a pulse train. Okay, the other name is comb of t. Okay, the signal looks like comb, so it is also called as comb of t. So by multiplying x of t by comb of t, you get another signal. Okay, where you have only the samples, only at these points you are having values, thereby you get a discrete time signal. Okay, so this signal will be called as x of n. So this is the simplest sampling process. Okay, so you do from now this CT signal is converted into a DT signal. Okay, but in doing so, there is a condition. Okay, because when you want to reconstruct the original signal, if you want to reconstruct the original signal from the sample signal, this is the sample signal, the third one is the sample signal. From this samples, if you want to get back this, okay, there is a condition. So that condition must be satisfied when you are doing the sampling. So the sampling theorem states that, okay, the sampling should be done at a particular rate. Okay, it should be done at a minimum rate, and that minimum rate is called as Nyquist rate. If it is not done at that minimum rate, then you will not be able to reconstruct the signal. Okay, this is the simple or colloquial way of telling the sampling theorem. Okay, when you are doing a sampling of an analog signal, you have to do it at a minimum rate. Okay, otherwise you will not be able to reconstruct the signal. So what is this minimum rate is? It should be twice that of the maximum frequency of the given signal. Okay, for example, see the signal. This signal doesn't, you cannot have a find out a frequency on seeing this. Maybe it is a composite signal which consists of many signals. Okay, so it is some f1 plus f2 plus f3 plus some signals. Combination of some signals makes this x of t, suppose. Okay, so if you are having a maximum frequency in this composite values in the different frequency components, the signal, the sampling frequency, or this frequency, the frequency of the sampling, what is it, pulses, must be at least twice that of the maximum frequency here. Okay, otherwise you will not be able to reconstruct it. Otherwise you will be having what's called as aliasing. You will have an error which is called as aliasing. Okay, so this is the statement for sampling theorem. A band limited signal can be reconstructed exactly if it is sampled at a rate at least twice the maximum frequency component in it. Okay, now the sampling theorem applies to what is called as a band limited signal. You cannot do it for any signal. Band limited signal means that should be a maximum frequency and that should be a minimum frequency. Okay, so this kind of, when you draw the spectrum in the frequency domain, it should be limited, okay, within a band. That is called as a band limited signal. So here the maximum frequency, the maximum angular frequency is omega m. We can say that the maximum linear frequency is fm. Okay, so for this the sampling rate must be at least greater than or equal to 2 into fm. Okay, 2 into fm, that is called as the sampling rate. Okay, okay, now I will come back to this this diagram later, and let me come to the notes I have written. Okay, so I have also stated here what is sampling theorem. Says that a composite signal, okay, a composite signal is a signal which has more than one frequency component. Okay, it is not a single frequency. You are having many frequencies added into that, and that is called as a composite signal. So a signal which has more than one frequency component is called as a composite signal. Okay, let us call it as x of t. Must be sampled at a rate at least twice that of the highest frequency in x of t for enabling proper reconstruction of the original signal from its samples. Okay, so this is the point. If you want to reconstruct it, you do the sampling properly. Otherwise, you will not be able to reconstruct your original signal. Okay. Okay. Now, suppose x of t is undersampled. Okay. Suppose if you do not follow this condition, if the sampling rate is less than 2 times of f max, then what is called as aliasing will occur. Okay. So what is aliasing? Aliasing is this. So alias means it is a false or assumed identity. Okay, alias means a false or assumed. You identify someone else for somebody else. Okay, so that is called as aliasing error. Okay, so in signal sampling, aliasing refers to one or more frequencies and sampled at a uniform rate fs would give the same set of sample values and thus might lead to incorrect reconstruction of the original signal. Okay, so in signal sampling, what is aliasing? One or more frequencies may have the same samples, okay, after being sampled by a signal frequency fs. Okay, hence the reconstruction may be a problem. Reconstruction of the original signal may be a problem. Okay, okay. Now see an example. We have an example here. So consider 3 sinusoids with 3 frequencies. Okay, this f1 is 60. Oh, sorry, this is not 600. It is 60. So consider 3 sinusoids with 3 frequencies. F1 is 60, F2 is 340, and F3 is 460 hertz. Okay, they are all sampled at a rate Fs is equal to 400 hertz. So what we'll see what will happen when these are all sampled at 400 hertz. Okay, so now the first frequency is 60. Let us write it as cos 2 pi 60 t plus pi by 3. Okay, that is the pi by 3 is the phase shift. Cos 2 pi 60 t pi by 3. Second sinusoid is cos 2 pi 340 t minus pi by 3, and the third one is cos 2 pi 460 t plus pi by 3. Okay, so these are the 3 signals, cosine waveforms. Okay, and these 3 are sampled individually by a sample frequency of 400 Hz. Okay, now let us see what happens when you sample these 3 signals with the same, or what is it, with the sampling frequency of 400 Hz. Okay, so now if you want to sample 60 Hz 400 hertz of sampling frequency is okay. If you want to sample 340 hertz, it should be minimum, the sampling frequency should be minimum 2 times this. Okay, so it must be 680. Okay, and for this it should be 920. Okay, this frequency 460 degree, the sampling rate should be 920, but all the three are sampled with 400 hertz. That means that there will be some aliasing problem. Okay, now first let us see the diagrammatic diagram of these signals. Okay, so this is the first signal. F1 is equal to 60 hertz. Sampling frequency is 400, and the second signal is F2 is 340 hertz. Sampling is same 400 hertz, and F3 is 460. Sampling is 400. Okay, see these two are not sampled as the required rate. Okay, they are undersampled. These things are undersampled. Okay, so now let us take the samples from these three waveforms. These three are the waveforms. Okay, a low frequency, another higher frequency. So we are taking samples at a rate of 400 hertz. That means 1 divided by 400 will be equal to 0.0025 seconds. Okay, so 0.0025 seconds is the time period for every sample. So once in 0.0025 seconds, we are taking a sample. Okay, so this is cos 2 pi 60t plus pi by 3. Okay, so there is a there is a lead of pi by 3. So phase shift of pi by 3 is there. So this is the first sample. Okay, next sample is taken as 0.0025 time t is equal to 0.0025 seconds. So this is the second sample. 0.005 seconds. This is the third sample, fourth sample, etc., etc., etc. Okay, so these are the samples you get. And now see the second diagram. This is the waveform. Okay, here there is a minus pi by 3 of phase shift. So it is here. Okay, it starts here. Instead of starting here, it starts here. This is the phase shift. And now you are having the sample starting from here, and for this is the same point. Okay, same time you are taking the same sample, the sample values is the same, and again you are taking the third sample, the sample value is the same, and fourth sample, the sample value is the same. Okay, fifth sample, the sample value is the same, and so on. So even if you sample 340 and 60, you are getting the same samples because the sampling frequency is not enough here. Okay, similarly for the third frequency 460 hertz, 460 into 2, it must be 920. Minimum sampling frequency must be 920, but you are sampling at 400 hertz, so definitely you will not get all the samples properly. Okay, so you are having first sample, second sample, third sample, and so on. Okay, but these things, when you use these samples for reconstructing, what you will get is you will not get back your 340 hertz, or you will not get your 460 hertz, but you will be getting your 60 hertz frequency. Okay, so now this 340 and 460 are called as aliases. Okay, otherwise 60 is called as the alias of 340. Okay, as and signal of 460 hertz. Okay, because they are undersampled. This condition occurs only when there is undersampling. Okay, undersampling is when you do the sampling with the frequency which is less than the Nyquist rate. Nyquist rate is nothing but the frequency which is equal to 2 times the maximum frequency in the composite signal. If it is a single frequency, it is just 2 times the frequency. If there are many frequencies in the signal, it is 2 times the maximum frequency. Okay. Okay. Let us come to the nodes. Okay, now mathematically also we can prove this, how they are becoming the aliases. Okay, now I have given the same thing. As the highest frequency is 460, you have to sample it with 920 for no aliasing problem, but now there is aliasing problem. Okay, now let us convert these discrete time signals into continuous time signals into discrete time signals. So cos 2 pi 60t, okay, will be now converted into what is it n into t. Okay, n into t is the sampling period. So this n into t, the sampling period is 1 by sampling frequency. So it is cos 2 pi 60 n by fs plus pi by 3. Okay, so what do you get is cos 0.3 pi n plus pi by 3. Okay. Okay. Now come to the second one. It is cos 2 pi 340 n by sampling frequency is 400. Okay. So 400 minus pi by 3. So now 340 divided by 400 into 2 pi, you are getting 17 by 10. That is 1.7 pi n. Okay, you can write it as cos 2 pi n minus what is it, 0.3 pi n, which is equal to cos 2 pi minus theta. You will have cos theta. So cos 0.3 pi n minus pi by 3. Okay, this is 1.7 pi. Okay, pi n. So you can write it as 2 pi n minus 0.3 pi n, which is nothing but cos 0.3 pi n minus pi by 3. Okay, now come to the third signal. X3 of n is equal to cos 2 pi 460 is the frequency, signal frequency, n divided by 400. Okay, again what do you get is what is it, 23 by 10 pi n. So it is 2 pi plus 0.3 pi. So it is again cos 0.3 pi n plus pi by 3. Okay, so in all the three cases, x1 of n is also cos 0.3 pi by n, that is the frequency, plus pi by 3, and then this is cos 0.3 pi n minus pi by 3 and cos 0.3 pi n plus pi by 3. So all the three signals become equal. Okay, initially it was cos 2 pi 60t plus pi by 3, cos 342 pi, what is it, 340 t and 460t. Now when you convert it into a discrete time signal, all the three has become the same signal. Okay, so this is called as aliasing. This is called as the aliasing problem. We have proved this, or we have seen this, what is it, mathematically. Okay, all the three signals are same, and we have I have shown you the diagrammatically also. I have shown you how all the three are equal. Okay, so now how to find out this aliasing frequency. So that is a simple formula. Okay, plus or minus, what are called as aliases? Plus or minus f naught. F naught is the signal frequency. Plus or minus k into fs. K is an integer. Fs is the sampling frequency. F naught is the signal frequency. Fs is the sampling frequency. Okay, so plus or minus f naught plus or minus k into fs are the possible aliasing frequencies. Okay, so now let us find out the alias for 340, 460. So for 460, f naught is 460, fs is 400. I can have f naught minus fs, 60 is an alias. Okay, 60 hertz is an alias. 340, I can again 60 becomes an alias because minus 340 plus 400 is again 60. So the 60 hertz is an alias of 460 hertz and 340 hertz if they are sampled with a sampling frequency of 400 hertz. Okay, this happens only because of the sampling frequency. So with the sampling frequency, this both are there. Okay, in the equation, plus or minus f naught plus or minus k into fs. Okay, these will give you the alias. So we can say that 340 and 460 are aliases of 60 hertz for fs of 400 hertz. Okay, so now you understood what is alias frequencies. Okay, okay. Now, when you draw the spectrum of this happens in the time domain. When you go to the spectrum of the discrete time sample signal, okay, this is also important. So when you draw the spectrum, you will be having what is it, images of your spectrum when it is sampled. Okay, so now you study where these images will occur. Okay, so a real-time sinusoid with the discrete time frequency omega naught cap, omega cap is equal to omega by f naught. Okay, the spectral lines will be at plus or minus omega naught. Okay, this is also omega naught. So if I have a frequency of f naught, and if you find out what is it, its angular frequency, you will be having your what is the spectrum? The spectrums at the angular frequencies. So if you if a discrete time signal is called as a cos omega naught n plus or minus pi, okay, you will have the spectrum at omega naught and minus omega naught also. Okay, and if the amplitude of the signal is A, this amplitude will be divided equally for both the frequencies, positive and negative frequencies. So here I'll have A by 2 and here I'll have A by 2. Okay, and frequency is in radians here. So in the spectrum, you have to mark your frequency in the x-axis, omega in the x-axis or f in the x-axis, and at the corresponding frequencies, you will be having a value. Okay, if there are many frequencies, many continuous frequencies, you will get a band, you will get a continuous band. Okay, so suppose if x of n is equal to cos 0.4 pi n. Okay, if it is cos 0.4 pi n, then at 0.4 pi and at minus 0.4 pi, you will have 6, okay, spectra with the amplitude of half and half here. So here the amplitude is 1 and these two amplitudes are half and half, 0.4 pi and minus 0.45 4 pi. Okay, now when there is aliasing, it is not properly sampled, when there is aliasing, okay, for omega cap for a single cosine signal, okay, then we'll have spectral lines, not only at omega plus or minus omega naught, but also at all plus or minus 2 pi L frequency offsets. You will have the spectral lines at the offsets, at the 2 pi L offsets. Okay, that is at plus or minus omega naught cap and plus or minus 2 pi L, where L is a positive integer. Okay, now let us see this. There is an alias here. So if I have a stick here, spectral stick here, omega naught cap, okay, at the offset after pi, this is pi and this is 2 pi, and from 2 pi, okay, you will have an what is it, 2 pi minus omega naught cap, you will have a stick, and then 2 pi plus omega naught cap, you will have a stick. Okay, and then here also 2 pi minus 2 pi plus omega naught cap minus 2 pi minus omega naught cap, you will be having sticks all over for an aliased signal, for a sample signal with aliasing. Okay, so the image at plus or minus omega naught cap repeats at every 2 pi offset, that is at omega naught plus or minus 2 pi L. Okay, here and then 2 pi minus 2 pi minus omega naught, 2 pi plus omega naught. Okay, this is minus 2 pi minus omega naught and minus 2 pi plus omega naught. Okay, with respect to pi, this distance, okay, this one has to be, there will be an offset. At the offset of here, you will have another stick. So this is what happens for the spectrum of a sample signal. Okay, so in this spectrum, 2 pi, okay, when you take a spectrum with respect to omega or in terms of pi, 2 pi refers to the sampling frequency fs and pi refers to the sampling frequency fs by 2 or fs by 2. So 2 pi always refers to fs. Okay, 2 pi is the last end. It will refer to fs by 2 and pi refers to, sorry, 2 pi refers to fs and pi refers to fs by 2. Okay. Okay, so fs by 2 is called as the folding frequency. Why it is called as the folding frequency is, here this folds. Okay, at pi refers to fs by 2. Here this fold, this one. Otherwise here it folds. That's why it is called as a folding frequency. So when you draw a spectrum for an undersample signal from minus pi to plus pi, the aliases fold back from plus or minus fs by 2 and fall within minus pi to plus pi. Okay, this is very, very important. Okay, pi refers to fs by 2, the frequency fs by 2. Okay, remember for your exam and all. Pi refers to the sampling frequency divided by 2. Okay, in the spectrum, okay, in terms of pi or in terms of omega, it refers to fs by 2, and the aliases will fold back. Okay, at fs by 2 it will fold back, it will take a mirror image, and it will fold back at fs by 2 plus or minus fs by 2, and all the aliases will also be available from minus pi to plus pi. If there are aliases, they'll all fold back and they'll fall within minus pi to plus pi. Okay. Okay, so this one you can yeah, you can analyze more and understand this concept and remember the formula for your exams. Okay, so yeah, this cat question is very simple only. If a periodic signal is decomposed into 5 sine waves of frequency, okay, 100, 300, 500, 700 and 900, what is the bandwidth? So bandwidth is always the range of frequencies which exist. So maximum frequency minus minimum frequency, or minimum to maximum is the bandwidth. So here the maximum is 900, minimum is 100, so the bandwidth is 800 hertz. Okay, now what is the spectrum? It is asked what is the spectrum. The spectrum is with respect to, you have to draw it with respect to frequency, and here the individual frequency components are clearly given. So you will have 6 at these frequencies. Okay, 100, 300, 500, 700 and 900, and at minus 100, minus 300, minus 500, minus 700 also you will be having values, and the value will be 10 divided by 2. Okay, I'm sorry, I made a mistake. 10 divided by 2 and so on. Okay, like this it will be 10 divided by 2. At everywhere it will be by 2, the amplitude by 2. Similarly on the other side at minus 100 I'll have a 10 by 2. Okay, 5, and then at minus 300 you will have another 5, 500 minus 500 you will have another 5, and so on. Okay, so this is called the spectrum. Okay, and the same signal, if the signal goes through another system which converts to a non-periodic composite signal, okay, but it has a bandwidth of 200k, it is having some frequencies up to 200k with a middle frequency of 140k. Bandwidth is 200, middle frequency is 140. So if the middle bandwidth is 200, so divided by 2 is 100, and middle frequency is 140. So it will extend from 140 plus 100 to 140 minus 100. Okay, so 40 to 240, okay, will be the frequency range, because it is given that middle frequency is 140 and the peak amplitude is 20 volts. So the two extreme frequencies will be 40 to 240, and it is given the maximum value is 20. Okay, maybe here also I think it should be 20 divided by 2. Oh, so this is the spectrum. It is not given the shape, okay, but it is given that at the ends it will be 0. It will come back to 0. The maximum value is 20. So what is it? Yeah, customarily drawn like this. So this is the spectrum of the signal. Okay, bandwidth. This is the middle frequency, and it total bandwidth is 200. So what is the Nyquist rate? This is the maximum frequency. 240 is this is a band limited signal from 40 to 240. So this is the maximum of frequency. So Nyquist rate will be maximum into 2. Okay, so 480 K is the Nyquist rate or minimum sampling rate. Okay. So first, when you see a sampling problem, first you have to see what are the frequency components available, whether it is a single frequency or composite signal. So if many frequency components are available, you have to take the maximum frequency, and maximum frequency into 2 will be the required sampling rate for no aliasing. Suppose the sampling rate is given less than that, there will be aliasing, then you must be able to find out the aliasing frequency. If the spectrum is given, the aliasing frequency will be lying within minus pi to plus pi. Okay, that is minus pi to plus pi refers to plus or minus fs by 2. Fs is the sampling frequency. Okay, so sampling, it will, all the aliases will have an image, okay, within the region minus pi to plus pi. You must be able to identify that. Okay, all the best. Bye.